Hey everybody, welcome to today's lesson. We are going to continue our discussion on solutions. Today we're going to be focusing on what's called a saturated versus unsaturated solution. But before we do that, I did want to just quickly run through some examples of Regents questions that you may or may not see based on just general solubility. So question number 1 asks, which compound is insoluble in water? Now, remember, prior to yesterday's lesson, we have basically defined solubility as being a black and white concept, just it is soluble, it is insoluble. And so when you see a question like this, you do have to remember that the reference table is there to help you. So solubility in water is a reference table. Okay, F question. And so we do need to pop over to reference table F. So we have calcium bromide, potassium bromide, silver bromide, and sodium bromide. Notice that all of these are bromide, which is going to make our life a little bit easier. So let's go ahead and pop into reference table F. Okay, here we have our solubility guidelines for aqueous solutions, and we are looking for bromide. Okay, so looking at ions that form soluble compounds, we're scanning down, and we note that we do in fact have halides here, okay, which does include bromide as an ion. So bromide is always soluble unless it is paired with silver, lead, or mercury. So we are looking for one of our solutions or one of our options in our answer choices to be silver bromide, lead bromide, or lead 2 bromide, sorry, or mercury 2 bromide. So let's go ahead and pop back over. So looking here, calcium bromide, potassium bromide, silver bromide. Okay, so that is our exception, our silver ions. So therefore it's insoluble. Question 2. The solubility of KCl solid in water depends on. So we are looking at factors that impact general solubility, okay, and specifically we have solid potassium chloride. And so does pressure impact solubility of solids? The answer is no. The rate of stirring. Now I want to be clear here. If I stir faster, the substance might dissolve quicker. But does that impact how much of a substance can be dissolved? And the answer is no. Okay, and so the rate of stirring might increase the rate of dissolution or the rate of dissolving, but it doesn't impact how much I can dissolve. The size of the KCl sample, solubility is a limit. Okay, there's a limit. I can dissolve X amount given X amount of water. So the size of my sample is not going to impact my solubility, but the temperature of the water does impact solubility. Remember, with solids, increased temp means increased solubility. Okay, all right, question 3. Under which conditions of temperature and pressure is a gas most soluble in water? So we are looking for gas solubility, most soluble. When I see questions about this, I always say think about soda. Right? If you're going to drink an ideal can of soda, you want it to be nice and cool because low temperatures keeps that delicious fizzy carbon dioxide in there. So we want low temperature and we want high pressure because again, if we pressurize the can, we're forcing more of that carbon dioxide into our solution. So low temperature, high pressure, think soda. And last but not least, at which temperature does, at which temperature can water contain the most dissolved oxygen at a pressure of 1 atmosphere? Okay, so we have 10 degrees, 20 degrees, 30 degrees, 40 degrees. Okay, oxygen, dissolved oxygen, is that a solid or a gas solute? Okay, that's going to be a gas solute, and therefore we want the lowest possible temperature, which is going to be 10 degrees Celsius. All right, excellent. So now what we're going to do is we're going to take a look at a quick simulation. And so let me go ahead and pull that up. I believe I have it in a different screen. Okay, So here we have cobalt chloride solute. Okay, it's considered a salt because it's an ionic compound. And I'm just going to go ahead and shake it into the water. Now notice that we see the water changing color because that solute is dissolving. Okay, and as we dissolve more of it, the color gets darker. And what I want to see here is that eventually, notice at the bottom of the solution, what do we see is building up? We notice that there is undissolved solute at the bottom of our solution. So let's go ahead and flip back and note that in our observations. So we saw that the salt or the cobalt 2 chloride dissolved and created a homogeneous solution. Okay, until it stopped dissolving at the bottom of the container. Okay, and so what we're going to be taking a look at today is why did that salt stop dissolving? Why does it just sit at the bottom of our container? All right, so let's go ahead and move forward. Now, something you may have noticed about that salt is that when it did stop dissolving, there was a term here that said saturated. Okay, it said saturated. And so it's important for us to go ahead and define what is a saturated solution. And a saturated solution, and much like the word, I tend to use an example of a sponge. I feel like you've heard the term of saturation with a sponge or saturation when adjusting color on images. Saturation means you're pulling it all the way up, or if a sponge is saturated, it's completely filled, right? It's completely filled with water. So a saturated solution is a solution which contains the max amount of solutes, okay, per given amount of solvent at a given temperature. So it's a lot of words, but essentially there's a limit to the amount of substance or solute you can dissolve in a given amount of water. So for example, if you have ever, maybe when you were first diving into drinking coffee or tea and you've tried to dissolve too much sugar into your coffee, there's a limit to the amount of sugar that can dissolve. And that is a saturated solution, right? That means it's completely absorbs all of the sugar it can take. It can't dissolve any more solution. Now, if I were to add more water, you'd probably be able to, or I'm sorry, add more coffee, you might be able to add more sugar. If I increase the temperature, again, we know that that could increase the amount of sugar that we can add. So it's a lot of words, but essentially there's a limit, and that would be a saturated solution. So we're going to use our solubility curves to help us determine a point of saturation. So here's an example of a solubility curve. I'm using this one specifically because the one that we use for class is significantly more complex. So this one only has 4 lines. So let's go ahead and take a look at a couple of things about the solubility curve. First and foremost, on this example of solubility curve, it does not start at 0. I didn't create the curve. I'm not sure why, so just make note of that. But also notice that, again, and I pointed this out in class, but our solubility curves are per given amount of solvent. So this is per 100 grams of water, and that's important to note. Additionally, you can see we have an increase in temperature. So question 1 about our solubility curve. How many grams of solute B would be needed in order to make a saturated solution at 100 degrees Celsius? Well, okay, so where do you think I'm going to find a point of saturation on my solubility curve? And if you're thinking it's probably on the line, you're right. Our line represents the point of saturation. So the lines represent saturation, okay? And so if I want to know how many grams of solute B is going to create a saturated solution at 100 degrees, I simply need to read up from 100, find my point B, and read across. Now, obviously, this is tricky, so we're going to make our best estimates based on this graph here. So I would say it doesn't quite hit 40. I would say maybe 38 grams or so. Again, there's usually a range that's accepted for these. So I don't know, let's say 37 grams of solute B would create a saturated solution at 100 degrees. Okay, instance or point 2. Okay, now instead of asking us how many grams we would be able to dissolve in order to make a saturated solution, they're telling us an amount of solute that's been added to the solution. So we have here 20 grams of solute A is dissolved at 80 degrees Celsius. Okay, great. So here's 80 degrees Celsius. Here's 20 grams. Here is where I'm currently at. That's what I've added. Okay, is this considered a saturated solution? Okay, the answer is no. Does it hit point A? Point A is all the way up here. So no, this is not a saturated solution, okay? Because we've added less than the maximum amount of solute. So how many more grams could we add in order to create a saturated solution? So what we would have to do here is read up to solute A and read across to find the point of saturation. So I would say that this is approximately 55 grams would be my point of saturation. I've added 20 grams, right, of solute A, and therefore I could add another 55 minus 20, and that would give me, I could add another 35 grams of solute A before it's saturated. Okay, so what is a solution called then if we have added less than the maximum amount of solute? Okay, so saturated means we've added the maximum, and an unsaturated solution means that we have added less than. So this is going to be a solution in which the max amount of solute has not been reached, okay, in a given amount of solvent at a given temperature. All right, again, a lot of words. If you want to simplify that for yourself, you totally can. But again, less than the maximum amount of solute has been added to this solution. So if we were looking at line A, and you can feel free to do this on yours if you'd like, or you can leave it as it is. I know we have quite a bit of stuff on our graph already, but I just want to point this out because we will have another graph to answer more questions below. Again, our line, for example, line A here, I'm going to do this all in terms of line A, but for line A, so in terms of line A, okay, in terms of line A, my point of saturation, again, is the line, right? That is the line. If we are looking at an unsaturated solution, then everything that falls below that line is going to be considered unsaturated. So this would be unsaturated. Okay, excellent. All right, so I just want to do a couple more questions with you just to practice using our solubility curves and just point out a couple more things that may or may not pop up when you're seeing these questions. So here we have a same curve, fresh curve. Okay, suppose I were to double the amount of water. Okay, I were to double the amount of solvent. So now I'm taking what was 100 grams and making that into 200 grams. Okay, what do you think that's going to do to the amount of solute that can be dissolved? Okay, if the solvent is doubled, okay, the solute is doubled. So therefore I can add double the amount that I normally would be able to. Okay, and so I want to point out that the Regents does like to be tricky here. They like to use 200 grams of water without telling you they've doubled it, just to try to trip you up. All right, suppose I were to half the amount of the solute. Okay, so I'm going to cut that in half to 50 grams. Okay, what would happen to the amount of a solute that can be dissolved? Okay, so if solvent is halved, okay, solute is halved. Okay, again, the Regents loves to use 50 grams of water without telling you they've halved it. You have to be able to turn that switch on in your brain and recognize that they're doing that. All right, let's get some more specific examples here then. So about how many grams of solute C can be dissolved if we use 200 grams of water at 0 degrees? And again, oops, I should have realized this when I wrote this sheet. There is no 0 degrees. Let's just change this to, let's assume that this is 40 degrees Celsius, and we'll just call this 40 degrees. Okay, so looking at this, we have double the amount of water, so whatever value we get, we're going to have to double it. So we're looking at solute C at 40 degrees. So I'm going to read up here to 40 degrees. I'm going to say this is approximately 15 grams. And so again, that'd be 15 grams per 100 grams of water, but I have 200 grams of water, and therefore 15 grams per 100 grams, therefore means I would have 30 grams per 200 grams. All right, why don't you try pausing the video and answering this next question before we go over it? So approximately how many grams of solute D can be dissolved into 50 grams of water at 50 degrees? So go ahead and pause and try this, and then we'll go over it together. All right, welcome back. Hopefully you paused. If you didn't, that's okay. So approximately how many grams of solute could be dissolved into 50 grams of water at 50 degrees? And we're looking again at solute D, 50 degrees Celsius. So looking at solute D at 50 degrees, reading upward here. Okay, Okay, we're gonna fall right about here. I'm going to say that's approximately 54 grams, again, per 100 grams of water. So looking again at solute D, we had 54 grams per 100 grams, and therefore we are looking at approximately half of that for 50 grams, or about 27 grams. Again, there's a range, so if you were off by 1 gram or so, that's totally fine. There is a range of answers that are usually accepted here. Okay, last question. Of the 4 substances, which is most likely a gas, and how do we know? So looking back, we have A, B, C, and D. And remember, we talked about this in class, but solid substances, solid solutes, with an increase in temperature, increase in solubility. So if it's a gas, an increase in temperature would cause it to decrease in solubility. And therefore, the only one of these would be D. D is our only option for a gas. So solution D. Okay, and again, as temp increases, okay, solubility decreases. Okay, everybody, that's it for today. I will see you guys tomorrow. Have a great rest of your day.